Hello everyone, my name is Sohrab and I'm a PhD student of Geotechnical Engineering at the University of Alberta under supervision of Dr. Henry and Dr. Macchiota. My research focuses on finding and developing new tools that can improve the landslides monitoring strategies. And today, as the title of my presentation suggests, I am going to talk about different ways we can convert the LOS velocity that InSAR gives us to the true velocity vectors. Remote sensing techniques have become an integrated component of landslide monitoring plans, and of such methods, InSAR has gained a considerable share of attention in the last decades. InSAR is favored in particular because of relatively lower associated costs and efforts than in-situ instruments, since InSAR can monitor a wider area with an acceptable accuracy and sampling frequency. But what is InSAR? The term stands for Interferometric Synthetic Aperture Radar, and the rather long name contains both an essential feature of the sensor and how it works. The SAR sensor is mounted on a satellite which orbits the globe at an altitude of about 800 km. The sensor constantly broadcasts microwaves to the ground. The objects on the ground, based on their electromagnetic properties and their geometrical shapes, start to refract and reflect the received waves, and the reflected portion of echoed waves will be stored by the sensor for each pixel. But let's not forget that the transmitted and backscattered pulses are waves, and so they have an amplitude and a phase like any other waves. The amplitude component looks like an aerial photograph, but the phase component looks very random, which is, I'm afraid, the part that we're mostly interested in. The next time the satellite is orbiting the Earth at about the same point, it repeats the same process and obtains a second phase scene. The analysis starts by stacking these phase scenes in a way that the corresponding pixels also correspond to a same footprint on the ground. If the phase values of the second scene is subtracted from the first scene, we will have a mesmerizing concentric pattern of circles that is called an interferogram, which is why the term interferometric appears in the term InSAR. For some applications, like characterizing faults, we stop here, but for uses like mapping movements for landslide monitoring, it's not the last step. There are different factors that contribute to make an interferogram, and ground deformation is actually one of them. So we usually try to minimize the impact of other factors, such as atmospheric effects, in order to obtain the velocity map. When we think about sending and receiving a signal, the most intuitive way to think about it is that it works like a camera. We shoot the signal and wait until we receive the backscattered wave through an always open diaphragm. You can see a very simplified geometry of the problem in the left figure, and using some trigonometry and a fancier equation that calculates the angular resolution, for a sensor at an altitude of about 800 km and a range of 3 to 5 meters for spatial resolution, along with the typical range of wavelengths for microwaves, the necessary aperture for this mechanism turns out to be at least 10 kilometers. To put it into scale, it is about 83 times a soccer field's length, which is obviously not feasible to launch and maintain such a large sensor in space. What radar experts did to tackle this challenge was using the Doppler effect. Instead of a single shoot of the beam and keep the diaphragm open constantly, they changed the sensor to switch between sending and receiving very frequently, on the order of microseconds. Because of the relative movement between the Earth and the satellite, and due to the Doppler effect, they saw at a certain point the resonated frequency reaches its peak, which should be theoretically the location of our target. This way, they could manage to decrease the radar length, or the sensor's aperture in fact, from 10 km to about 10 meters, which is 1,000 times better. This signal processing trick led them to synthesize the aperture, and that is why part of this technology's name is synthetic aperture radar, or SAR. InSAR is a very robust all-day, all-weather tool for landslide monitoring, but it has a very crucial drawback that limits its further incorporation into the monitoring systems. In the left figure, you see a GPS unit installed on a block of rock that is moving downslope as much as the pink vector shows. If we process the SAR scenes obtained over this block, the deformation would be less than that and would match with the blue vector much better. This is because InSAR is only capable of picking up the displacement along the sensor's line of sight, or LOS. This LOS measurement adds a considerable ambiguity into both magnitude and the direction of movements and leads to representation of landslides kinematic that is less intuitively understandable. Let's take a look at our imaginary valley on the right side. The white vectors are the true velocities and the yellow ones are the LOS measurements of that satellite. You can see that the yellow vectors are not quite truthful to the white vectors. They can be very different in direction and of course magnitude. Even worse, due to the satellite's looking geometry, active regions may appear as a staple, for example, for that vector in the red rectangle. This becomes a significant issue when setting alarm thresholds for velocity or acceleration in a monitoring system for regions that hosts several landslides moving at different rates and directions, or even for a single landslide with different slope aspects. So, numerous techniques have been proposed in the literature to decompose the LOS velocity into 3D, which eventually gives us a true total velocity. And I'm going to start with one of the early suggested methods. By having the geometry of LOS, we can establish the mathematical formula to correlate the LOS velocity with the vertical, eastward, and northward velocity components, as you can see in equation 1. But it is not the only relationship we have, because satellites pass a point sometimes in the ascending direction when orbiting from South Pole to North Pole, and sometimes in the descending direction when orbiting from North Pole to South Pole. As a result, we have two sets of LOS velocities, which helps us to set up the system of equation, as you can see in equation 2. This, however, is still an ill-posed problem because we have three unknowns that are components of velocities and only two knowns, ascending and descending LOS velocities. Many studies suggested to simply discard the northward component because the satellite orbits are near polar and so they are almost unsighted to the northward component. This discarding implies that we are assuming the northward component to be zero, so this method becomes more reasonable for phenomena that does not involve much of a movement in south-north direction, such as ground subsidence or even landslides moving primarily in east-west direction. But please note that the satellite is almost unsighted to this component, and if it was completely unsighted to this component, this velocity component wouldn't appear in the calculations, and assuming so would induce an error into other components. Other studies instead pursued different approaches. They incorporated additional information which can be provided by these three avenues. 1. Using other variants of InSAR analysis. 2. Using in situ measurements. And 3. Exercising topography-informed assumptions. The first group of methods analyze SAR scenes differently so we can get the velocity along the satellite's flight direction, or so-called azimuthal velocity. These methods are not good enough in terms of accuracy, and they're also very computationally demanding and work better for broader targets such as glaciers. In the second category of methods, external sources of information such as GPS or GNSS units are used to help the interpretations, but in situ units are very sparse and sophisticated mathematics are needed to mitigate the impact of this shortfall. Finally, the last approach is employing a topography-informed assumption. Since the landslide processes and the superficial geometry of the ground have a symbiosis, the geometry can be leveraged to take inspirations for establishing an assumption about the direction of true velocity vector, and that is what I looked into. The most famous of all topography-informed assumptions is surface parallel flow method, or SPFM, which was originally introduced for monitoring glaciers, but then many others used it for landslides, and today the general belief is that this is a fair assumption for gravity-driven phenomena. It assumes that the velocity should be parallel to the terrain, and equation 4 is its mathematical form that uses the elevation gradients in east-west and south-north directions, which leads to a new system of equations as equation 5 shows. The second method is aspect parallel flow method, or APFM, that only poses an assumption on eastward and northward components in a way that be parallel to the aspect of the slope. The third method is the steepest terrain following method, or STFM, which combines the mathematical assumptions of the other two, so only one set of line-of-sight velocities would be needed to perform decomposition using this method. After a literature review, it came to our attention that they are often used arbitrarily, and little insights on the performance of each of these methods exist, especially in the context of translational landslides. So the objective of this study was finding the advantages and disadvantages of these three topography-informed assumptions, especially to evaluate their accuracy in interpreting the magnitude, aspect, and travel angles of velocity vectors. To achieve these, I conducted a comprehensive InSAR analysis using SAR scenes archived by two sensors, 243 Sentinel-1 scenes in ascending and descending direction, as well as 202 RadarSat-2 scenes in two different beams were used. You can see more details about the spatial resolution, geometry of acquisition, revisiting time, and the sensing period in Table 1. For each of the three assumptions, SPFM, APFM, and STFM, two different iterations were considered, so in iterations number 2, more Sentinel-1 images are involved. Thus, in total, 6 iterations were set up and then decomposed by their corresponding assumption. The study site chosen for this investigation was Thompson River Valley, located in Canadian Cordillera between Ashcroft Town and Spence Bridge in the province of British Columbia. A long history of landslides has been documented within a 10-kilometer section of this valley, and the left figure shows the location of all these cases. The tracks of both the Canadian Pacific Railway and Canadian National Railway pass through this corridor and traverse 12 of these 14 landslides. The landslides along the valley have a retrogressive behavior and typically move at rates less than 200 mm per year. The superficial geology of this valley comprises of quaternary deposits formed by a series of glaciations. Geological studies in the area identified several formations overlying andesitic bedrock as seen in the right figure, and previous studies found that a weak, highly plastic clay seam within the unit number 2, that is at the residual stage with a friction angle of about 10 degrees, accommodates the subhorizontal basal shear surface of landslide in this valley. It is now known that the river elevation is the main factor contributing to the activity state of the slopes through backward gradients caused by drawdown. Among all, the Ripley landslide is one of the smallest but the most heavily instrumented one, with its rates sometimes reaching to 2 mm per day in the short term. Its movements have been monitored using a variety of superficial and subsurface instruments such as shape axle arrays, slope inclinometers, GPS units, and corner reflectors. 3 GPS units are installed at the site with GPS 1 and 2 being close to the CP tracks, and a third one on the retaining wall between CP and CN tracks. You can see their location and the average velocities measured from April 2008 to February 2020 in this figure. You can see that GPS 1 and 2 are traveling at the aspect of 62 to 66 degrees northwest at a travel angle of 14 to 17 degrees, while GPS 3 is illustrating a more pronounced total velocity of 117 millimeter per year. It is theorized that GPS 3 is situated on a different block than the other two, and it is also under some localized effects, and so GPS 1 and 2 were only used for this study. The framework I used for this investigation had two parallel streams of calculations. First one starts with analyzing 4 stacks of SAR scenes, which yields the LOS velocities at 4 different viewing geometries. Then, using these values, the mentioned 6 iterations were set up so I could perform the decomposition using the assumptions of SPFM, APFM, and STFM. The magnitude, aspect, and travel angle of vectors at the location of GPS units were then compared against the measured values by GPS units to calculate the error in each of these parameters, which will be referred to as direct analysis error. The other stream starts with back projecting the GPS velocities on the satellite's LOS, setting up the iterations pool, and decomposing them once again. The back projection error then was calculated by comparing the final results against the values reported by GPS units. The nice thing about back projection analysis is that it provides an opportunity to study the accuracy of methods in an isolated situation when only and only the accuracies of topography-informed assumptions are involved and other exogenous sources of variances are excluded. However, direct analysis is as important because obviously it is a reflective of the impact of all the practical limitations such as the efficiency of InSAR analysis algorithms or the spatial resolution of scenes. In this table, you can see the direct analysis error as well as back projection error in the magnitude of the total velocity average for the location of GPS 1 and 2. It is seen in direct analysis error in iterations number 1, APFM with the error of 15 millimeter per year, which is 18% of GPS reported velocities, is the most accurate assumption, followed by the other methods. In iterations number 2, the error values are universally increased compared to the counterpart in iteration number 1, because more Sentinel-1 scenes are involved, which highlights the importance of using scenes with finer spatial resolutions. The back projection analysis also confirmed a similar trend of ranking between accuracy of these methods, that APFM is the most accurate assumption. The performance of these methods cannot be solely judged by looking at the magnitude of velocities because an underestimation of one component may be counterbalanced by overestimation of another component and eventually giving rather same accuracy in the magnitude. But even the slightest inaccurate estimation of one component is always manifested as a geometrical alteration. This table shows the accuracy of each of these topography-informed assumptions as revealed by the direct and back projection analysis, with the large errors being underlined. You can see that APFM and STFM are both accurate enough in interpreting the aspect angle with an error of maximum 7 degrees. But it seems that SPFM predicts the aspect angle at the GPS locations far off from the true values, with errors from 20 reaching up to 36 degrees. SPFM is nevertheless successful in interpreting the travel angle similar to STFM. But it is APFM this time that suffers from large errors in travel angle. By looking at the map of the vectors and the distribution of their geometry and magnitude, we can realize that the performance of these methods as I presented in the previous table, is not only limited to the location of GPS units. The far left bottom figure shows that blue bars, which belong to SPFM, is more biased toward north, while the other two are much closer to the direction that the GPS units would suggest. Right next to it, the distribution of travel angles also displays that red bars, which belong to APFM, are showing an over-steepened interpretation. I was curious to investigate if this is an arbitrary effect only observed at Ripley landslide for whatever unknown reason or not. I will not get into the journey I took to investigate the root cause of these behaviors, but after developing some new mathematical methodologies, we observed that these are not random effects, but in fact they stem from the very mathematical core of the assumptions. In short, we found that LOS errors when using SPFM and APFM are reflected as geometry distortions. In conclusion, a hybrid approach is suggested for performing the decomposition, so the APFM is used for calculating the magnitude and aspect angle of vectors, but SPFM is used for estimating the travel angle. I believe this would conclude the main part of my presentation. However, I'd like to take a minute and talk about the next phase of my research. One of the goals of performing LOS decomposition and using other instruments to monitor the ground movement is that so we can forecast the failure time. It is a common practice to use the inverse velocity method to this end, but there are other methods as well to deliver this task, and it is not clear which one is the most accurate one. So I gathered more than 80 time series displacements or velocity values of historical failures, and I'm going to perform forecasting 3 methods by inverse velocity, SLO, and velocity over acceleration methods. In the end, I'd like to thank our supporters and collaborators, Natural Sciences and Engineering Research Council of Canada, CP, Transport Canada, Queen's University, and of course, Geological Survey of Canada. Thank you very much for your attention, and I'll be more than happy to answer any questions you may have.
Sohrab, can you just confirm that you hear us, and so we can also confirm we can hear you? Great.
Yes, loud and clear.
Thank you. So I'll put it out to the audience. Are there any questions about Sohrab's presentation? David.
Yeah, just are there what's the limitations on InSAR versus movement? Like, is there a upper and lower limit for movement? Like I know if it can be moving too quickly, the I guess what do we know what those limits are, or is that something that's being tested, or?
So if I understood your question correctly, you're asking about the upper lower limits of the accuracy of estimations by InSAR, right?
No, the actual whether it's feasible for the upper and lower limits for the actual movement of the slope being able to be monitored by InSAR.
So displacement rates, I believe.
Yes.
Yeah, I think, well, there are a couple of different parameters that play, like they contribute to the answer of your question, because we have different conditions such as the vegetation, the wavelength of the sensor, as well as the rate of the movements of the slope itself. But for like using the regular Sentinel-1, for example, the C-band sensors with a minimum vegetation, theoretically it is possible to pick up the displacements as slow as, for example, 2-3 millimeters per year. For better targets such as man-made structures, we had a better luck of picking up slower displacements and slower velocities, such as like as low as 1 millimeter per year for Oldman River Dam. Well, if it's going to be very fast moving slope, I think a shorter wavelength would be better, for example. But for typical landslides that we see in Thompson River Valley, I think C-band sensors are like such as Sentinel-1 and the RadarSat-2 are quite good, and they can be performing in the range of I believe 20 millimeter per year to 300 millimeter per year, perhaps.
Okay, well, thank you. And I guess then with that, is there any possibility of utilizing the InSAR with the Assiniboine River?
Well,
is that-
yeah, yeah, like for like in last year's RGHRP presentation, I presented a bit of InSAR work on the Assiniboine River Valley as well. But for this site, the one thing that was very you know, causing a problem was the vegetation there. You know, the vegetation is a bit more in the Assiniboine River Valley compared to the Thompson River Valley, with shrubs and trees and everything on the side. So I think down the road we probably need to install some corner reflectors at the Assiniboine River Valley to pick up displacements better.
Okay, no, that's what I was going to say. If we can get some reflectors on site, then maybe that's something that we can utilize to double check the methods too.
Yeah, of course.
Actually, that we do intend to eventually get out to
Okay.
the Assiniboine, but certainly we're not going to do much with 2 or 3. It'd be much better to get a more substantial network. Similarly, we've got the corner reflectors at Ripley, but we're also beginning to install a network on the north slide as well.
Okay.
With a slightly different model of reflector with snow cone, which will allow us to monitor through the winter at both sites, which for the Assiniboine is probably going to be quite significant improvement for full season monitoring.
Perfect. No, but that's something we can chat about tomorrow, I guess.
Yeah.
Great.
Yeah.
Yeah, sounds good. Are there any other questions? Chris?
Just going back to David's first question, Sohrab, were there any periods, did you look at the 2017 acceleration of the Ripley slide versus your InSAR data to see if you could detect those fastest movements, I'll call them? Were those still detectable with I think it's a 12-day window you guys have on the InSAR data?
That's a great question, actually. So for very short periods of acceleration, the one thing with InSAR is that we will not be able to use the multi-temporal InSAR analysis, and then we have to come back to the differential InSAR analysis, in which we use 2 scenes of SAR's acquisition, actually. And the problem with the InSAR differential InSAR analysis is that that method is very, it's more susceptible to the atmospheric effects, and would lower the accuracy of estimations from millimetric to centimetric. But to be specific, I haven't done the InSAR analysis on the 2017 acceleration for Ripley, but that's definitely one of the end games in using the InSAR and monitoring the Thompson River Valley to pick up the accelerations as well in the window length of 12 days, as you mentioned. But not at this moment. Yeah, I haven't done analysis yet.
Thanks, Sohrab. Great work. Really, really interesting.
Great.
Thank you.